Welcome to this session on queuing systems. Now, you must have witnessed that when you visit a bank or a post office, or for that matter of fact, at different places where public service systems are installed, then you have to often face being in a queue or a waiting line. So for example, you have some work to be done at a bank, then you will approach the bank branch, and then at the counter there will be a queue. You will be standing in line. One by one, the bank official or the customer, the concerned bank teller will be processing the various service requests from the customers, and one by one they will be processed, and when your turn arrives, your request is also processed. So this is a typical representation of such a queuing system, wherein we have different components, like the calling population is there. Basically the calling population is one that places a demand and uses the deployed capacity at any production or operations system. Now then one by one the customers requests or the jobs will be processed after they have been into a waiting line by the server. Their requests will be processed, and then the served customers will leave the queue. So this is a typical representation of a queuing system. Now there is a what is the need for us to study these queuing systems, which are also called the waiting line models. So the waiting line models make use of queuing theory fundamentals to analyze the impact of alternative capacity choices on important operational measures in operational systems, such as the queue length, waiting time, and the utilization of resources. Now consider a capacity planning problem in case of a computerized railway passenger reservations facility or system at one of the Indian Railways stations. Now in simple terms, we'll have to find an answer to a quick key question, that how do we decide the number of booking counters to be made available to the public at such reservation booking counters. So in case there are too few counters, then definitely customers will be standing in long queues, and that will impact the service quality. The customers won't feel satisfied by if they are made to wait. So how do we decide on the number of counters available at such service systems or places? A similar thing can be seen at a banking system also, or a BSNL paying bill payment system counters also, or even at post offices. So in service systems, waiting time is an important operational measures, because it is directly a reflection of the service quality. If you are good at quality and perceived so by customers, then you need not make the customer wait in long queues and for long durations. And apart from the service systems, similar examples exist in manufacturing systems also. So suppose you have in your production or operational manufacturing facility some resources which are very few, and they are highly utilized. Then these resources or these machines or these work centers might become a bottleneck, and in case they are too few in number, then there might be cases when long queues of jobs pile up, and because of this there will be pile up of the inventory, and this will lead to missing of the delivery commitments and shipping delays in an organization. So the waiting line models are an important concept which makes use of queuing theory fundamentals, and they will be studying typically the queue length, the waiting time, the jobs or the customers are spending in queues, then what is the utilization of resources, and based on these they will try to analyze the impact of different alternative capacity choices, so that the best can be selected for the perspective of operational measures in any operational or production system. Now coming to a bit more details about queuing systems, then there are certain main components which are studied in queuing systems, and these components are called as the calling population, arrival parameters, queuing parameters, system structure and parameters, service parameters, and performance metrics. Now when we talk about the calling population, it is basically that population which places the demand and uses the deployed capacity in any production or operation system. Now there might be cases when this calling population is infinite. For example, if we consider the petrol pump in a metro city like Delhi, then there will be a large number of vehicles plying in Delhi, which belong to Delhi or which are coming from outside also, and they might be using this facility. So there is a large number of customers which will be there. We can relate it, or we can approximate it like being an infinite calling population. Similarly, for metropolitan bank branch, like a branch in maybe Mumbai or Chennai, the calling population will be several those individuals or institutional members which are residing in society in that particular city like Mumbai or Chennai. So this again typically amount to being considered as infinite number as far as the operational systems are concerned. Now there may be some cases when the calling population might be finite also. For example, if for example in a manufacturing facility, say consider there are 300 machine tools in the plant. So for maintenance department of that organization, these 300 machine tools will be the calling population. It will be a fixed number. So if any request for maintenance comes to the maintenance department, it will be basically from these 300 machine tools which are there at the operational unit. So it is a finite calling population. Now there is another important component which is the arrival parameters. So typically we are more concerned with the arrival rate of customers or jobs at a production or operations facility. So at what rate the customers or the jobs are arriving, and then what is the pattern of arrival of customers. So are they arriving as single units or single jobs, or they are arriving in bulk units? So or there are some arrangements or in which the special kind of groups are arriving. The special groups example can be a case like we have the say in case of you can consider the case of like typically flights the customers take. So when they arrive at the airport, if there are frequent flyers, then they will be issued, or maybe there are members of special privileges membership card they have been given, like gold, platinum cards. For based on that they can be treated differently, means they might not have to stand in the regular queue, and they can jump they can stand in a special queue, so that they are processed their requests are processed fast. So you would have considered this or seen this often in case of the boarding pass issue counters at the airports of different airlines. So that kind of arrangement might also be there. Then when we talk about the arrival rate, it is often represented by some prominent distributions like the Markovian distribution or general distribution or the deterministic distribution. There are the most commonly employed distribution for modeling the arrivals in a waiting line problem are the Poisson and exponential distributions. We'll see more of more characteristics of these distributions in subsequent slide, but basically the number of arrivals per unit time is often found to follow a Poisson distribution. So based on experience and statistical studies, we can say that the number of arrivals per unit time is often found to be following a Poisson distribution. Whereas when we consider the inter-arrival time, that is between successive arrivals, what is the time? Then that is found to be following exponential distribution function. So we'll discuss more of it in subsequent slide. Then there is another important component called the queuing parameter, Q parameter, and often like we have the different scheduling algorithms like the first come first serve basis or last come first serve basis or random. Similarly here also we have the queue parameters. So depending on the customer's queue, the first customer which is arriving, it is processed first, then the next customer which is arriving, it is processed next. So that is an example of first come first serve arrangement. And it might happen that the last come first serve arrangement is there, wherein the customer who arrives last, it is the first one to be processed. So then there can be random order also of processing the customers which are there in the waiting line. So these are called as queue parameters. Then there are another important component called the system structure and parameters. So this is represented based on the number of servers which are there, whether there is single server or multiple server, or whether there is a single system stage system in an operational unit, or there is a multiple stage system. Then how the routing, whether it is a single serial or network kind of routing of jobs that is followed in that queuing system, and what is the capacity, whether it is finite or infinite to process the various jobs or customer requests. So based on that we consider the system structure and parameters. Then there are some service parameters also, which are represented through prominent statistical distributions like Markovian general and deterministic distribution. Then the queuing model performance is often measured in terms of various performance metrics such as the queue length, the waiting time, the utilization rate of servers, and the cost. So we'll see more of it in subsequent slide. To consider first when we talked about the different system structure. So when we talk about the system structure, it basically refers to the manner in which the resources are organized in the operating system. So we might have a single server, single stage system, wherein there is a single waiting line of customers and they are processed by a single server, and once they are processed they move out from the system. So this is a typical example of a single server, single stage system. There is a single server and it is organized, the server is organized as a single stage. Then there is another category, which is the single server multiple stages system, in which there are several stages. So as we can see, there are 3 stages here shown. The first stage, one server, second stage is also having one server, and third stage is also having one server. So customers will be waiting in the waiting line, arriving and waiting in the waiting line. They will go to the first server. The server 1 will process the request, and then subsequently there will be a processing requirement by the second stage server also, and then so on for the third stage server also. And once all the processing is done, then the customer leaves the system. So this is an example of 3-stage single server system. Now we can also have multiple servers single stage system, in which there are multiple servers but they are at the single stage. So this can be also seen at say typical bank branch. When you arrive, there will be many counters which are processing customer requests. So for say if some customers arrive and they want to get the checkbook issued or want to get the draft issued, so there will be multiple customer counters which are doing the same job, same kind of tasks, and the customers will stand in line, and one by one the counters will get they will be directed to the counters and where there is request will be served. So we have single stage, but there are multiple servers involved in such case, and hence it is called multiple server single stage system. This is arrangement is also seen in at the passport offices in India. That there is a waiting queue, and then depending on your number, coupon token number, you go to the respective counters where they process the different your application for passport. So after this there is another category which is called the multiple server multiple stages system, in which we have again the customers arriving, standing in a waiting line, and then they are marked diverted to the different servers. So there will be multiple servers at each stage. So like here there are 3 stages: stage 1, stage 2 and stage 3, and each stage is having 3 servers. So since there are multiple stages and within each stage there are multiple servers, so it is called a multiple server multiple stage system. Some prominent terminology is associated, or symbols are associated when we study a single server system, queue system. So one is the LS. Now LS stands for the average number of customers in the system. These customers are standing in the system waiting to be served, and the average number of such customers is given by is represented by the symbol LS. Then the average number of customers in the waiting line is represented by the symbol LQ, and WS symbol represents the average time a customer spends in the system. So this average time is given by WS is given by the sum of the waiting time plus the time taken during service of that particular customer request. Then there is the symbol WQ, which represents the average time a customer spends waiting in a line. The symbol lambda represents the mean arrival rates, like how many customers are arriving per hour. That is represented by the symbol called lambda. Now mu symbol represents the mean service rate, which means how many customers are getting processed by a particular server per hour. So that average figure number, that is represented by the symbol mu, and it means the mean service rate. Now if there are n number of servers, multiple servers in a multiple server queue, then the number of servers in that multiple server queue is represented by the symbol S. Now coming to a single server queue system, which follows exponential distribution of service times. The average number of customers in the waiting line, that is LQ, in such cases of single server queue, is given by the symbol lambda square by mu into mu minus lambda, where mu and lambda mean that mu mean represents the mean service rate and the lambda represents the mean arrival rate. These have been arrived at statistically, mathematically, and this formula is often used in queuing system. Then there are some other common performance metrics or measures which are used in queuing systems. One is the server utilization, and in case of a single server system, the server utilization is represented by the symbol rho, and it is given by lambda by mu, where lambda is the mean arrival rate and mu is the, as we have seen already, the mean service rate. Similarly, for multiple server systems, the server utilization is represented by lambda by S into mu, where the symbols mean the same thing. Usually S represents the number of servers. Now there is a Little's formula which is represented by a set of equations. So one is the equation for WS, that is the average time customer spends in the system, and that is given by LS divided by lambda. LS we have already seen. What does LS mean? LS means the average number of customers in the system which are waiting to be served, and lambda represents the mean arrival rate. Now then the average time customer spends in the queue, WQ, is represented by LQ by lambda. Now LQ we have already seen that it is represented, it represents the average number of customers in the waiting line, and mu represents the lambda represents the mean arrival rate of customers in the queuing system. Now in case of single server system, the average number of customers in the system is given by equation LS is equal to LQ plus lambda by mu. So these are some standardized symbols. Now as we studied that the Poisson distribution and exponential distribution are very particularly important when we talk about the queuing systems or queuing models. So typically in a Poisson distribution, what happens is that the probability of the number of arrivals, that is of customers or jobs, during any given time t is given by this equation. That probability of n number of customers arriving at time t is given by lambda t raised to the power n into multiplied by e raised to the power lambda t divided by factorial n. So where lambda means the mean arrival rate, t is the time, n is the number of customers, the probability number of customers or arrivals for which the probability is to be found out. E represents the symbol E standard 2.718, that is the standard representation when you talk about exponential series, and lambda and t again the same. Factorial n represents the factorial of a number n, that is the number of arrivals of customers or jobs. So the factorial n, like when we talk about factorial 5, so it is given by the given by 5 multiplied by 4 by multiplied by 3 into 2. So any number multiplied by subsequent smaller numbers till we reach 1. That gives us the factorial of a number. So factorial of 3 is 3 into 2 into 1, that is 6. Factorial of 4 is 4 into 3 into 2 into 1, so that is 24. So and so forth, for any n number n, factorial can be found out. Now in Poisson distribution, the mean of Poisson distribution is given by lambda, and variance also is given by lambda. When we talk about exponential distribution, then in case of exponential distributions, the probability of an arrival within a specified time can be computed with the help of the probability density function, which is given by the ft, gives the probability density function, which is given by ft is equal to lambda into e raised to power minus lambda t, where the symbols have usual meaning. Lambda is for the mean arrival rate, and e is 2.718, that is exponent's value of standard symbol, and then t represents the specified time. In the case of exponential distribution, the mean of exponential distribution is given by the 1 by lambda. So the mean of exponential distribution is given by the symbol lambda, and the variance of exponential distribution is given by the symbol given by 1 by lambda square. So these are some standardized means equations which have been derived, and it represents based on the different pattern of distributions. So these represent some specific important parameters for Poisson and exponential distribution, and hence we have taken a look at it here. Now consider an example to develop better understanding about the concepts which we have studied so far. So suppose there is a bank counter or a teller facility at a bank, and that counter has one man, one bank official, which is processing the customer requests. Now the customers are given to arrive at that bank counter at the rate of 1 every 4 minutes. Means one customer is arriving 4 minutes, so in 1 hour how many will arrive? It will be 60 divided by 4, that is 15 customers on an average arrive every hour at that counter. Now the service time is given to be random, and based on the past observations, it is said that on an average that particular counter official takes 3 minutes to process one customer request. So 3 minutes on an average is taken for processing one customer. So in 1 hour it will be 60 divided by 3 is equal to 20 customers. So 20 customers on an average will be processed, or service request will be done by that bank counter. Now we have to calculate the probability, that what is the probability that there are at most 3 customers in front of that teller or counter. So when we say at most 3, means there can be 3 or less than 3, which represent they can be either 3, they can be, or they can be 2, or there can be 1, or there can be no customers. So what is the probability that there will be 3 customers, or what is the probability there will be 2 customers? If we sum all these up, probability of 3 customers, probability of 2 customers, probability of 1 customer, and probability of no customers, then we get the answer to this first part. Then there is in the second part there is to be assessed the various operational performance parameters for that teller counter at the bank branch. Now then it is also given that of late the bank officials have noticed that the arrival rate has slightly changed. So earlier one customer was arriving every 4 minutes, now the one customer is arriving every 3.5 minutes. So it has, arrival rate has slightly increased. So what will be the impact of this change in the arrival rate, so on different performance parameters? So that is to be assessed in this particular question. So as we have seen, the arrival rate will be given by that is if there is one customer is arriving every 4 minutes, so in 1 hour 60 by 4, that is 15 per hour will be the mean arrival rate. Similarly, the service rate will be 20 per hour, because one customer request is being serviced in 3 minutes. So for every hour 20 customer requests will be on an average processed. The utilization facility rho is given by the equation rho is equal to lambda by mu. If we put the values of lambda and mu, so we get 0.75 as the server teller facility utilization, which means that basically 75% of the teller facility is being utilized. Now the probability that there will be 3 customers at most at the teller facility, that will be given by the sum of the probabilities that there will be 3 customers, or there will be 2, or there will 3 customers plus there will be 2 customers plus there will be 1 customers, or plus 1 there will be no customers. So it is a possibility that there is no customers, or there can be 1 customer at any given point of time, or there can be 2 customers in the queue, or maybe 3 customers. So when we sum all these individual probabilities, we get the probability that at most there are 3 customers in the system. Now using the formulas which we have studied previously for the Poisson distribution expression. So for Poisson distribution, the arrivals is given, the probability of arrival of n customers is given by this formula. So you will use this formula, and using this we will calculate the probabilities, and then sum of the probability, individual probabilities for 1 customers, 2 and 3 customers will be giving us the answer. So probability of 0 customers is given by, so this is equation for Poisson distribution, which is given in the earlier slide which we have just seen. So we will be utilizing that, and we compute the value of probabilities for n is varying between 0 to 3. So the first is for a single customers being there, and we get the probability as 0.25. For getting 1 customers in the queuing system, we calculate the probability using the same equation, this particular formula. We calculate and we get as 0.1875. Then for having 2 customers in the queue, the probability is 0.1406, and having 3 customers in the queue, the probability is 0.1055. If we sum these probabilities, we get 0.6836, or there is 68.36% chance that there will be at most 3 customers in the queue in this case, in the given example. Now using the different formulas, like prominent formulas we studied, and earlier we'll calculate for in this case, so we get the average number of customers in the waiting line, that is LQ, as 2 points. So on an average, around 2 customers, around just over 2 customers, maybe 2 to 3 customers will be there in the waiting line. Then the average number of customers in the system will be given by LS is equal to LQ plus lambda by Q. When we put the values, we get the value of 3. So we can expect that about 3 customers will be there on average in the queue system. Now the average time a customer spends in the line, waiting in the line, is given by WQ is equal to LQ by lambda. When we put the values of LQ and lambda, we get the 0.15 hour, means roughly 9 minutes on an average every customer is spending waiting in line in this particular example of bank teller facility. And now the average number time a customer spends in the system, WS, is given by LS by lambda, and when we calculate it, we get it as 0.2 hours or 12 minutes. So average time which a customer is spending is given by 12 minutes. So 9 minutes he is spending waiting in line, and for rest 3 minutes his service request is getting processed. So eventually 12 minutes time he is spending in the entire queuing system. So we have put these calculated values over here, and then it is given in the last part of the question that since the arrival rate has changed slightly, that now 1 customer is arriving every 3.5 minutes instead of 1 customer arriving in 4 minutes, so the arrival rate has slightly increased. So with the increase in arrival rate, what will be the values of these calculated parameters, performance indices? So when we calculate them again with the because in this case lambda will become then 60 by 3.5, so it will be 17.14 instead of earlier lambda value of 15. With that value of lambda, when we calculate the performance parameters, then we'll get these values. So now we see that the utilization has increased from 75% to 85% when the arrival rate increases slightly. Now at the same time, the average number of customers in the waiting line has grown from 2.25 to 5/5. So more customers are now waiting in the queue as the arrival rate of customers has increased. Similarly, the average number of customers in the system has also increased, rather it has doubled. So earlier there were just 3 customers on an average in the system. Now in this case there will be 6 customers on an average in the system. Then the average time a customer is spending waiting in line has also just doubled or increased from 9 minutes to 18 minutes when the arrival rate has slightly increased. And then the average time a customer spends in the system has also increased from 12 minutes to 21 minutes. So the arrival rate has impacted the performance parameters significantly. Now we often plot that how the operational performance measures will vary according to the utilization. So as we saw in just this previous example, the utilization from 75% to 85.7%, when this happens, then all the parameters change, performance parameters. So if we plot the parameters, then what we see is that as the utilization of servers increases, then what trend we see is the operational measures, performance measures trend. What we see is that it follows this kind of increasing trend. Means when there is low utilization, we have a high cost of operation and good service. So service is good, but there is a high cost of operation. But when we increase the utilization of servers, means as we use more and more of server, then that is a case of high utilization, and this high utilization decreases the cost of operation because we are utilizing the same facility more. So basically your overall costs per unit of manufacturing or per unit of servicing customers is coming down, but at the same time the service will be poor because there will be long queue in which the customer will have to wait. So as we see that when the service utilization, the utilization of teller counter increases, the customers which are in the queue increases, their waiting time in queue also increases. On an average processing time the customer gets processed, that also increases. So the service will be impacted, means it will be moving towards poorer service as the utilization increases. Similarly, if we study the expected costs, then we see that the waiting costs follow this pattern, that as the level of service is high, then the waiting costs are high for an organization. The service cost follows an increasing trend, and if we sum those two, then we get the total cost. So the total cost, as the level of service increases, first they tend to decrease and then they tend to increase. So this is a typical graph which shows a relationship between the level of service which a particular organization wants to offer and how much excess cost will be incurred for providing that kind of a service. With this we conclude this concept of queuing systems which are relevant for operations and production systems. Thank you.